Understanding and imitating human-robot motion with restricted visual fields. Consider a scenario of a human driving a car. As we can see in the video, the human has to check their rear view mirror and blind spots before changing the lanes. The human has limited field of view and therefore they have to look around to gain more information about the environment. Similarly, when making a U-turn, the human has to look in all directions and make sure it is safe to do so. To better understand such human-like behaviors, we consider robotic agents with limited observation capabilities. The agent is tasked to navigate in an environment with obstacles. The agent has a conical field of view parameterized by the radius and angle of cone. Furthermore, just like human, the agent can turn its head around to detect more obstacles. Also, we assume that the agent can miss out on obstacles even when they are present in their field of view, just like humans. And based on its observation, the agents plan its motion to move around in the environment. To better model, predict, and learn such human-like behaviors, it is necessary to reason about the observation model of the agent and their policies. The problem that we want to solve is, we want to look at the behavior of such agent moving in environments and infer the following quantities from the robotic agent's motion. The first one is the parameters of the observation space, the probability of detecting obstacles within agent's field of view, and the agent's motion policy pi. Our key idea is that we want to analyze the influence of each component independently by adopting a modular approach. We estimate each unknown parameter while assuming that the other two are known. In a simulation setting, we collect a bunch of demonstration trajectories of such an agent navigating through an environment with obstacles. We collect these demonstration trajectories and use these trajectories to estimate the observation space of the agent via first order methods such as Bayesian optimization or cross entropy method. And as we can see, we can closely estimate the agent's observation space. And then using these estimated values, we generate predicted trajectories to see how far these predicted trajectories are from the actual trajectories, and we observe that our predicted trajectories using estimated parameters are within 5% distance of the actual trajectories. Furthermore, we also use these demonstration trajectories to predict the observation space of the agent, and using the estimated values we generated predicted trajectories to see that predicted trajectories are within 5% distance of the actual trajectories. Furthermore, we also estimate the motion policy of the agent and approximate it as a diffusion policy. We observe that the predicted trajectories are within 3.5% distance of the actual trajectories. This is where the power of modular approach shows up. Our learned policy is not specific to a particular observation space on which it is trained and can be used for agents with different observation space as well. This would not have been possible for an end-to-end policy. Furthermore, we collect real human data using a game environment where humans are tasked with moving to their goal while avoiding obstacles, as can be seen in the video. Using this collected human data, we train a diffusion policy to imitate human behavior, and as shown in this videos qualitatively, our method is able to approximate human behavior very well. Furthermore, we also showcase that our method generalizes well to unknown environments and can detect obstacles and navigate around obstacles. Finally, we employ our learned policy from human data onto a robotic car to showcase the real-time capabilities of our method in real scenarios. As we can see, just like human, the robotic car is able to look around in the environment, detect obstacles, and avoid them successfully. In conclusion, we solve the problem of inferring the motion of agent by reasoning about its observation model. And our key idea is to isolate each component's effect by estimating one parameter at a time while keeping others fixed. Uh, and in future, we hope to explore ways to improve out of distribution performance. Thank you.